So we have modules 6 and 7. And that's data link layer. And associated with the data link layer is switches. So we will talk about those two topics. And module 7 is the next module for physical labs. So we'll do those here in class on Wednesday. Apparently, communication got scrambled with Brendan on how I wanted you to, let's say, let me know that you did the labs. Really, I'm not going to take the labs from your notebook, or that wasn't my intention, and go through them and, you know, read your answers and stuff. If you're if you are going, if you're, you know, doing the lab and you don't know what they want in some of the questions, you don't know how to answer, but you want to know, then just, we have like, sometimes I look at the question, I don't know what they want either, to be honest, because it's not always, you know, sometimes people that write those questions, the labs, maybe it's ambiguous or just unclear. Anyway, we have the instructor version that has, you know, what it is they're looking for. But I don't, that's not something that I grade. I just want to make sure you're doing them. Because it's, you know, it's helpful, very helpful to do the physical labs, not just the packet tracer labs.
So how do we let you know that we're doing them?
Okay, so I've got a notebook back there that's got a page for each student. I don't have your names in there, so there's a place for you to put your name. And then there's a checklist of all the labs that we're doing here in class. So that's all I want is when you come in here to do labs, whether it's on a regular Wednesday that we're doing labs in class, or you do them on a Saturday or any other time, you do the lab and you go to find your name in the in that notebook, and you know, ideally somebody's here to, you know, sign off on it, basically put their initials in that they, you know, saw that you did the lab. But if nobody happens to be here, which should be a rare situation, you know, just put your name in there, or just not your name, but just check off the lab, or put a note. There's a little note section, a note column, and you can just say, you know, I did this lab, nobody was here. So we know. That's all I want. I just, basically, it's just a, did you do them or not? And that's what you'll get the lab part of the physical lab part of the grade for. So that goes for the Zoom people too. So there's, when you come in to do your labs, on whenever you do it, whether it's a Saturday or one of these other open lab times, if you haven't already, you know, put your name on one of the sheets, then do that the next time. And, you know, whatever labs you do, we'll just check them off. And for those that did, you know, the module 2 labs, I think Brendan collected them from your notebooks. I'll actually give them back to you, but I'll use those to go and fill in, you know, the little check sheet up to now. So that way on Wednesday, you just have to do module 7. And we'll check those off on Wednesday, and on Zoom people whenever you end up doing them. So if for those in Zoom, if you have not come in yet to do labs, this would be a good week to do that at the end of this week on Saturday, and just knock off module 2 and module 7 physical labs all at once. If you've already done module 2, great. The next physical labs, we do have one for next, for module 10, which is in week 5, because we're going to do 3 modules next week. At least we're going to try to. If we get behind, we'll just push module 10 to the following week. But in any case, you don't want to have to try to do too many in one sitting, is the point, because you'll rush through them and you'll get less out of it. So if you get module 2 and 7, I'm talking to the Zoom people, if you get 2 and 7 done this week, then in 2 more weeks, you can do 10 and 11, because there's labs in 11 as well. Two labs in 11, or 1 in 11, 1 in 12. So, okay, and that's actually when we're going to be doing subnetting stuff. I thought it was earlier than that. Wow, module 11. They do the number systems right up front, but then wait a long time before we get back into subnetting. Yeah.
Sorry, so you just said we're gonna do subnetting when?
Looks like the subnetting section is going to be associated with module 11.
Okay, so I don't need to freak out that I don't know subnetting yet, because
Not yet.
Okay, that happened.
But you might, I mean, we're going to spend time learning it. So, but like I said, not as much time on the basics as CNT 101, because we have this new topic, it's not really new. It's just an extension of subnetting. VLSM just means variable length subnet masks. It sounds more scary than it really is. It's really just taking subnetting and in one phrase, it's subnetting a subnet. That's all. So you've subnetted, you've got a subnet, and you subnetted again. That's all. It's not really anything different. No, not a different process or anything like that. But I'll show you, some examples of doing that and how to go through. Like when you're given a network, the reason that you subnet a subnet is because you're going to get networks. You might have an inner network that needs 6 subnets, and 2 of them might have 100 hosts on them, and the others might just have a few, like 16 or 14 or 20. Well, you don't need the same subnet mask for 14 hosts as you do for 100. You're just wasting addresses if you do that, and you might not even have enough address space, because if you've got a Class C network, you only have 254 addresses total. If 2 of your subnets have 100 hosts on them, then really that's it. You can only create two subnets, because you've got that 200 hosts with a slash, what would that be? A slash 25, just 1 bit, create 2 subnets, and you're done. So you can then with VLSM, you can take a larger subnet, and if you don't need that many hosts, you can subnet it again to create additional smaller subnets. Anyway, we're getting way ahead of ourselves. So, because we'll probably say that whole thing again in a few weeks from now.
I hope I understand it then.
What's that?
I hope I understand it then.
Okay. Hopefully you will, because it'll be more methodical when we talk about it the next time.
Like in 101, we didn't spend any time on it. It was over.
Yeah. That's unfortunate, because that's one of the big reasons for the prerequisite. Not the only reason, but a reason for having a prerequisite. But that, we'll probably just, sometimes that happens when you have a new instructor. They're not sure what the you know, what they need to focus on the class necessarily. And so we'll get that straightened out for the future, hopefully. Okay, let's, any questions before we move on to module 6? All right. Grab. Okay, data link layer. So what can somebody tell me about the data link layer? Like what type of information is found at the data link layer? Okay, so the PDU is called a frame. Good, that's one thing. And what is what's in that frame? What's in that frame header?
Checksum.
There is a checksum, right? That's actually in the trailer, but yeah,
The MAC address
In
is
the
for
MAC
the source and
addresses.
destination.
source and destination MAC addresses. So actually destination first and then source. And then there's like a 16-bit field after the MAC addresses that is like it's a heads up to the network layer as to what's inside this frame. Basically, there's a little 16-bit field that called the protocol field. In other different variations, different types of network protocols, it might be used for something else. Like I think in IPX SPX, it's used as a length field to say how long the packet is, how many bytes are in the packet. But in TCP/IP, IPv4 networking, the frame header as a destination source MAC address, and then a type field that says what protocol is inside the frame. Okay, so we'll talk about the purpose of it, topologies, and a little bit about the frame and the data itself. So you might look at the data link layer primarily as it's used to deliver information to a particular device. Okay, so IP can't do that. IP address by itself can't be used. You know, you couldn't just send a packet out onto the network with just IP addresses, because how does the data get into any type of computer, any type of device? Through what? Goes through the NIC. Well, it's the NIC's job to decide whether to read the data in at all or not. And the NIC doesn't have access to IP addresses on the device. It only has access to its own address, which is its MAC address. So the only way that information is getting into the computer is if the destination MAC address, the destination address, matches the computer's, the network interface of the computer's MAC address, or it's a special frame like a broadcast, and some multicasts might also be read in. So device delivering the information to a device is the responsibility of the data link layer. And of course, you know, the data link layer header encapsulates IP header or the packet basically encapsulates the packet. So it gives the upper layers a way to access the media and actually get their data to the end device. Error detection does not do any error correction except the rare case of collisions. When we talk about errors in a frame, we're talking usually that are detected by the data link layer, essentially by the NIC, is going to be like checks or CRC errors, where the data has been somehow scrambled between the source and the destination. If the CRC remember the CRC gets calculated before the frame gets sent and it gets added to the trailer. And then when it gets to the destination, the NIC, before it ever sends it up to the upper layers, it does the same calculation and creates, another value, the CRC value, and compares what is in the frame with its own calculation. And if they don't match, it just rejects the frame. There's no telling the source, hey, there was an error here. It just throws it away. And it's up to the upper layers to recover from errors. If something like that occurs, data link layer is not going to fix it. It's up to the upper layers to somehow detect that not all the data was received and do some sort of resend mechanism. Like I said, the only correction that layer 2 does is in the event of collisions. So collisions are detected by the fact that in a half duplex connection, half duplex simply means I can send or I can receive, but not at the same time. So if I'm sending and I hear some chatting going on my receive lines, then that's the definition of a collision in a half duplex twisted pair. If you go way back to coaxial cable, the collision was real. I mean, the bits collided. With twisted pair, since they're separate, lines for transmit and receive, the bits never see each other. So it's listen while you're sending. And if you hear something, then that means somebody else sent as well. And that's means a collision. With coaxial cable, it was basically detected because it was a rise in voltage beyond normal, beyond the normal voltages that bits would generate. Because if bits collide, somebody's transmitting this way, somebody's transmitting this way, let's say they're 1 bits, just because that would, make a voltage level that would be beyond the tolerances, you would get, let's say 5 volts and 5 volts, you get 10 volts, and that would be seen by the network interface, and it would know that that means a collision. So that's why they call it a collision in the first place. And that's why we even have the whole idea of, collisions and half duplex, because in original Ethernet, it was just a single conductor, just a coaxial cable that had a single conductor for transmit and receive. And you couldn't do both at the same time because of that. Okay. Yeah, that's about it. The other types of errors besides CRC errors would be the really, bad errors like a malformed frame, which is usually a frame that's less than 64 bytes, which is referred to as a runt usually, or a fragment, a frame fragment, or bigger than the maximum allowed. If the maximum allowed on the media is 1518, which is typical for Ethernet, and it's bigger than that. If the frame is bigger than that, then it's referred to as a giant. But either way, it's an invalid frame and it gets tossed.
All right, what's a giant frame? How many?
More than the maximum transmission unit for the media, which is in Ethernet. Standard Ethernet is 1518 bytes. And if the frame is bigger than that, then it's somehow a damaged frame. Shouldn't be. Or it could be that somebody has turned on jumbo frames on their device and none of the other devices support that. Jumbo is a valid, jumbo frames are a valid Ethernet configuration, but everybody's got to support it. Everybody's got to be running jumbo frames so that everyone knows, oh, okay, we're allowed to have 9,000 byte frames instead of these little 1,500 byte frames. Well, it would come into play is if if that's what you wanted for your network, if you're like, I want our network to be fast, and sending 9,000 bytes at a time versus 1,500 would make it faster, considerably faster. Sure. Because a lot less overhead. You only have one set of headers for 9,000 bytes if you're sending big files. But then you'd have to make sure that every device not only supports it and supports it in the same way, because it's just not a standard that has ever been, caught on really well. So,
sort what kind of company or like situation would that call for, like, to do that?
I don't know. I mean, anybody that wants just
faster.
Yeah, lots. If you were sending lots of large files through the network, you're doing streaming video or high definition graphics, or anytime where you're dealing with large chunks of data or even big data, if you're sending big database files across the network. Yeah.
Is the configuration the only reason why the jumbo frames hasn't caught on, or?
As far as I know, the other thing would be is that I think once you get out to the internet, and since the internet is, you never know what's out there. There's all different types of media that's used and maximum transmission units. And so 9,000 most likely would then have to be, the packets would have to be fragmented along the line. And fragmentation is never a good thing. It usually, because if a fragmented packet doesn't have a way to be put back together if it comes out of order. Okay. Unlike a segment, a TCP segment, where it's got has a number associated with each segment in case they come out of order. But a packet that arrives, if the transport layer sends down because it saw that the maximum transmission unit was 9,000 bytes, so it sends down a 9,000 byte segment. Okay, that 9,000 bytes has a serial number associated with it. So the next 9,000 byte packet or segment, if they arrived out of order, they could be put back in the right order, okay? But once they get down to the data link layer, packet layer, and the data link layer, now if they come across a media that doesn't support 9,000 bytes, now it supports only, a regular Ethernet 1,500. Now that 9,000 bytes is going to have to be chopped up into 6 1,500 byte frames. And if those arrive out of order, you're out of luck because they're not serialized.
Gotcha.
So are most devices, computers and routers and switches and everything, are they capable of handling those jumbo things and just have to be configured to?
It's a good question to say most. I think most modern ones probably, but do they do it the same way is a big question. And, and again, it might work fine within your network, but once you go out to the internet, then, things get a lot.
So really, it would be pretty exclusive.
It would be exclusive to your internetwork. And then probably you'd want, instead of, letting the router, because it would have to be the router that's connected to the internet. That's the last device that then has to go across media that doesn't support 9,000 byte frames, maybe something much smaller, then it's gonna have to do the fragmentation. And now it's going out to the internet, and that's where you most need to have, numbered segments so they could be put back together. So you probably want to have something that then took these packets and turned them back into serialized segments. And that seems like a lot of overhead too. So yeah, I think, having this kind of deal with, large jumbo frames would be something if you really needed it and it just internal, and then you'd have to figure out how to deal with the internet. Okay. Slow as that. Okay, so make sure I didn't skip something. I did. Okay, so the data link layer by the IEEE, which essentially they're the people that define Ethernet with the 802.3 standard. They broke the data link layer up into two sublayers. And essentially they did that because this can be looked at as hardware. This is kind of, the job of the NIC, the network interface. And this is more of a software function. It might be more the job of the device driver that, talks to the NIC. And it also is the kind of the relay between the hardware and the IP, the upper layers, the network layer and above. So, so they broke that up, and I think primarily, to make it easier to design network interfaces. This is what you have to do in the hardware. This is what you have, what your drivers have to look like, or something similar. So just kind of remember that the LLC, logical link control, and MAC. So MAC sublayer is closest to the physical, and that kind of makes sense because that the MAC address is also the physical address. And so it's going to be closer to the physical. Logical link control, that word logical, we've also talked about layer 3 addresses as being logical addresses, not just IP, but the logical addresses. So that's the way to kind of keep them straight as to which one's on the top and which one's on the bottom. And these standards, 802.3, 802.11, you should know what really these three should be. If someone were to ask, or if it was on a test or something, you should know what those three broad standards apply to: Ethernet, wireless, and wired Ethernet, wireless, and basically Bluetooth. And does anyone know 802, where does 802, the number 802 come from? It actually means something.
Isn't it like the 802 project or something?
Well, it is the 802 project, but what does 802 mean?
Date? Was it a date?
Huh?
Was it a date?
February 1980.
That's right. Oh,
Yeah.
yeah.
So that tells you how long ago, how old Ethernet is. Ethernet started really, being codified by IEEE in February of 1980.
So is that in Europe then? Because it's backwards.
Maybe they were in France at the time. I don't know. I mean, IEEE is a worldwide organization, so they might have used, let's say the more common one, I think, because I think the United States way of doing dates is actually less common than the rest of the world. So anyway, And then the number after the dot is just, the section of that document. So 802, basically, not all, like WLANs weren't started in February of 80, but they fell under the same basic category as Ethernet, because wireless LANs are just Ethernet with an extra header on them. And of course, without the a slightly different physical layer. But other than that, the frames look all the same. You can capture wireless LAN stuff with Wireshark, and it looks pretty much the same, except you've got an extra set of headers, which is the header that says, the address of the access point, pretty much. Okay. What about this? Yeah. So I think, based just on the chart, you can see the MAC sublayer communicates with the physical layer. The LLC communicates with the upper layers, with the software layers, the protocols, IP for the most part. So now that LLC sublayer, it wasn't always just IP, and I guess it doesn't have to be even today. So the LLC sublayer was also responsible for basically knowing what the next layer is. Didn't have to be IP, it could be IPX if you were running Novell NetWare. It could be even NetBEUI, the older Windows protocol. So, and it could have been, what else? Oh, Apple Talk, yeah, that would be the other one. So that was the other thing that was responsible, is kind of what the logical layer was above it. Okay, so providing access to the media. Yeah, I've got a animation for this. Where did it- oh, there it is. Now I just gotta make sure that volume is set and everything. Oop. Okay, volume is set there. There. Okay. So yeah, how a NIC works.
Incoming data, these signals travel along the medium and receive that medium. The secrets formatted in the frame. CRC is calculated compared to the CRC frame tree. They don't match. The frame is damaged or changed when the frame is displayed. The situation is rare and happens in those environments where the medium is poorly terminated. If the CRC is okay, the destination MAC address is checked. Matches the NIC's burned in address or the broadcast. The frame is processed. Otherwise, it's displayed. Once the MAC address is verified, the frame header and trailer are stripped, creating a packet, which is sent to the network protocol for the process. The NIC's job is done. Now, for outgoing data, the reverse process occurs. The network protocol transfers a packet to the NIC. The NIC adds the source and destination MAC address as the frame header and calculates the CRC for the trailer. The frame is ready to transmit. The NIC converts the frame for transmission onto the medium disconnect signals.
Okay, so just Okay, so the other thing that we have to remember about the data link layer is that whenever a packet, let's say, where the IP address, the destination is a different network than the source, it's going to go through a router. And every time a packet hits a router, then the data link layer is going to be changed. Because the router now has to, so the fact that it got to the router in the first place meant that if my machine is sending to some remote network, the source MAC is going to be my computer's MAC. The destination will be the router. Once it gets to the router, and the router looks at its routing table and says, okay, I have to send this to the next upstream router, then it strips the data link layer header, puts its own MAC address as the source, and puts the next router's MAC address as the destination, recalculates the CRC, and then sends it off. And for every router along the path, some sort of de-encapsulation and re-encapsulation occurs in order to get the inner packet to its final destination network. So the frame headers change at every hop. A hop being defined as a router or a layer 3 device that it goes through. And but the network, the inner packet stuff never changes. Now there's exceptions to that. And some people might say, well, what about network address translation and stuff like that? Well, we'll talk about those later. Network address translation occurs usually in just one place, and that's the outgoing router. And in that case, inner packet does get changed. But in typical, non-NAT related communication, only the data link headers get changed. Yeah.
And at each hop, the CRCs checked.
It's checked, yes, and recalculated. Yeah, that at every hop, the router has to, before the router will do anything with the incoming frame. I mean, this is really just a function of the network interface. The route, not even the layer 3 stuff of a router. Because again, you think of a router as just a specialized computer. It's got a NIC, although, usually 2 or more NICs. And once the frame gets to the router network interface, before it even gets to the upper layers of the routing software, the NIC will check the CRC. And if it's no good, then it just throws the frame away, just like a computer would, a regular desktop computer. But if it is good, then it has to see, where do I put, what do I do with this packet? Do I send it out another one of my interfaces to, the destination LAN, or do I send it to another router? In any case, it's going to create a new frame header and recalculate the CRC before it sends it. Okay. Okay, physical topologies. I think you probably learned about physical and logical topologies, so there's not that much to say about them. We're just going to go over quickly the main topologies used in networking, and really some that aren't used very much anymore, if at all. But remember, the physical is just how the cabling is arranged. And so the most common physical topology is what? Star network, yes. Everything here is a star because, all the cabling goes to a single central point. And that's pretty, there's probably the second most common topology is going to be point to point, where you've got a wide area network situation, or even a wireless. You might have a point-to-point where two buildings are communicating. They couldn't or didn't want to run cabling between the buildings. And so they use wireless on the, antennas on the top of the building. And it's just a point-to-point type of topology between those two devices. And most WANs are also, well, not necessarily most, but a lot of WANs are point-to-point as well. You also have point-to-multi-point and so forth. Anyway, so that's the arrangement of the media. And then the logical topology is how the data actually moves once it's in the device. So we say when we're using, so really the logical topology is strictly dependent on what type of device you're using. Like in a star network, we're using a switch. So the logical topology is just it's just referred to as switched. Whereas if it was a hub, going back to the old days, the logical topology would be a bus. Because with a bus, the data goes out to all ports. Whatever incoming port it enters, it gets repeated out to all ports. So that's a bus. Whereas a switch, it only goes out the port that the destination can be found. And then the third one, that most common one you'd find with a physical star, would be a ring topology, like with token ring. And that's where the data literally travels in a ring from port to port to port to see, basically who should this be delivered to, and whichever port, has the ID that is in the header of the frame, then it gets read by that port. If that port, if it's not destined for that port just sends it on to the next port, and so forth. So that's your ring topology. So an extended stars, it's just stars connected together. And then bus, where everybody hears all the data. So your hubs, coaxial cable are both bus logical topologies. And then your ring. So not really much more to say about those. All right, full and half duplex. Half duplex, you can talk and not listen. You can talk or listen, but not both at the same time. So think two-way radio, press to talk. While you're pressing that button, you can't hear. So if somebody's talking to you while you've got that button pressed because you want to talk, you won't hear them, and they won't hear you either. So that's half duplex, well described as a two-way radio. And full duplex is more like a telephone. You can both be talking at each other at the same time. May not necessarily understand what each other is saying, but you can at least hear it. So that's full duplex communication. Hubs always work in half duplex, although you aren't likely to see hubs in practice anymore. Obviously, coaxial cable, coaxial networks are also half duplex. And then switches are full duplex, although they can operate in half duplex. You could go into the Cisco switch, go into the interface and say duplex half. I think that might be the command. It's been a long time since I played around with the duplex mode. But you can do that if you really wanted to. And then, you're basically crippling your network, because whatever you plug into it will probably do the auto detection of what mode and speed the switch port is running at, and it will copy it and go to half duplex if that's what's running. So But usually there's no reason to do that. The only time where you would want to actually force a port to half duplex is if whatever you're plugging into the switch only operates in half duplex and for some reason doesn't have the ability. Well, if it only operates in half duplex, it probably doesn't have any sort of auto negotiation capability anyway. So if you had some really rare old device that only did half duplex, then you would possibly likely have to force your switch port. Remember, you can do it port by port. You don't have to, you don't do the whole switch and set it to half duplex, just each individual port. Okay, access control methods, contention-based is the most, the original sort of Ethernet and continues to be the method type that's used with Wi-Fi. CSMA-CD, you probably saw that when you were talking about Ethernet. Carrier sense means listen. Multiple access means, that's what the MA means. Carrier sense, listen. Multiple access means, well, you're listening because somebody else might be transmitting. So that's what the MA means, that somebody else could be out there. And then if that happens, that you listened, nobody was there, and both of you did the same thing at the same time, and so you both thought it was okay to send, then that's why you have collision detection, is in that event. And if you have enough computers on a single half duplex network, you will get collisions eventually. I mean, it actually is more rare than you might expect. When we do the labs in here in 101 anyway, we try to make collisions happen. And I found that at 100 megabits, it's really hard with just with only 2 computers or 3, I guess you might have. It's really hard to get a collision to happen. Set it down to 10 megabits and you might get some. What you do, if you just really want to, see a collision happen is, set it down to 10 megabits and then make the ping packets as big as they possibly can be, which is, some thousands of bytes. There's some maximum, I don't remember what it is, but it's tens of thousands of bytes. And then, just keep sending them, so that they never stop. And you will start to see collisions if you do that, even with just 2 or 3 computers eventually. But, if you have 100 computers, then you're going to start to see collisions a lot. They're more or less a thing of a past, thank goodness, though. So we rarely, CSMA-CD is built into Ethernet. It's part of the IEEE 802.3 standard. So every NIC manufacturer, except for 10 gig, if you're a 10 gig NIC manufacturer, you don't need to worry about CSMA-CD because 10 gig is defined as full duplex only. So full duplex, the definition of full duplex is CSMA-CD is turned off. Basically when you're in full duplex mode, CSMA-CD isn't part of the equation. And so that's, the typical situation nowadays. On Wi-Fi, it's a different story because, Wi-Fi, even though they're starting to develop with the newer Wi-Fi standards, multiple channel Wi-Fi, and so you can have multiple conversations. So they're starting to look more like switches in a way, but they're still not quite really there. And so you still need this CSMA collision avoidance. And it's really, I don't know, I guess they changed the name because they just wanted to, it is a different process than CSMA-CD, but it's not so different than collision detection. Yeah.
So is access control used for half duplex? Like does full duplex not have access control methods?
full duplex. Yeah, as far as accessing the media, no, they don't, as soon as a frame is ready, boom, it gets sent. No, there's no need to listen because it's allowed, full duplex, it's allowed that you can receive while you're sending. So it's no sense in listening first because, you know, well, you're always listening, actually. You're always listening because it's full duplex, so you might be receiving a frame at any given time. Yeah, so there is no real access method with full duplex. And then, okay, so again, with CSMA-CA, the collision avoidance, I think I actually have both an Ethernet and a Wi-Fi thing for that. I think maybe earlier. Where is it? Ah, here we go. So CSMA-CD.
This simulation shows how we can network using CSMA-CD media access control and network uses a function. Computer 1 is a frame server. Computer 1 was first listened to the other stations transmit. This is the carrier sense part of CSMA-CD. No network activity is detected, so computer 1 sends the frame and is received by server 1. The server 1 receives the frame and creates a response. However, computer 3 also has data sent to server 1. Computer 3 and server 1 both listen to the media and detect the activity. The both computers send the frame. Rules of CSMA-CD say when one computer at a time is in data using the hub. Computer 3 and server 1 can listen to the media. They detect network activity after they finish sending the collisions. Collisions detected by all computers in the collision domain, causing all computers to pause for a random amount of time before attempting to send in the frames. In this case, server 1 tries first and they send its frame. Since no activity is detected, the frame is sent successfully. Computer 3 is now producing the frame. Remember, the collisions rarely occur in network technical switches, and not at all with all computers up to the computer duplexing. So while you may not need to be concerned about collisions in most networks, the obvious performance degradation of campus collisions helps explain why switches were developed to replace others.
Okay, so as you saw, they put some mitigating techniques into CSMA-CD to, you know, so that when a collision occurs, you don't just get collisions happening over and over and over again. In big enough networks that can happen, but you know, with the fact that they all wait a random period of time after a collision is detected, all the computers that are in the collision domain know that the collision occurred. So they all start this timer, and whoever's timer goes off first, you know, gets to send. However, you know, in a big enough network, you still can get multiple collisions. And again, I think I mentioned this the other day, that once 15 collisions in a row have occurred by, you know, a single machine trying to transmit, if it can't transmit 15 times in a row, then it basically says the network is timed out, and some error occurs, and then a user has to, you know, do something, usually restart the connection or something.
But all of that happens in milliseconds, right? So it's all still going pretty fast.
Yeah. Oh yeah. It happens microseconds. Yeah.
Oh, is it micro?
Yeah.
Oh, okay.
Yeah, if you think about 10 megabits, that's 10 million bits per second. So that's 1/10 of a microsecond for each bit. So it's pretty, and that's the slowest form of
Right.
Ethernet. Yeah. Whoops. Next. So here's a slightly different how wireless LANs do their CSMA-CA.
Wi-Fi operation is carrier sense multiple access, version avoidance access. In computer one, send the data from computer four. The first listens, senses the data, and shows three. The media is busy, station three. The media is free. Computer one transmits the frame to computer four. The access point receives the message and a single name of the piece. Computer four receives the frame while computers two and three respond. Computer four then sends the acknowledgement frame. Computer one will verify the frame is received successfully. In advanced operation,
So you can see why wireless, even if it's running at the same bits per second as wired, it's still going to be slower because you have these acknowledgements, which, you know, it basically, they basically say, take the bits per second and have it. And that's your actual, you know, bandwidth of a wireless network. Now, it could be that in some of the more current specifications that some of this has been improved. I have not, to be honest, kept up with the AC. I read about it a bit, know a little bit about it, but I don't know that many details of some of the underlying performance improvements that they may have made. So if anyone knows of anything, that contradicts this process on some of the more newer standards, feel free to speak up. That's something that I probably should go and spend some time looking at, but I just haven't.
this mode is usually only supported by higher Wi-Fi bands, and it's usually stations are located far apart, or used to the node top. In this mode, computer one again will three, computer one must, in a sense, ask permission to transmit by sending a request to send message to the access point. The access point to plot to the clearest limits the medium limit is clear. CTS message is heard by all other stations, notifying them that another station is about to transmit, and they must wait before attempting it. The amount of time they wait is part of the CTS message. Wi-Fi operations.
I was
Organs.
I goofed here.
This mode is usually stations are located far apart.
Okay, so what this is talking about is the standard CSMA-CA depends on the idea that all nodes that are in the connected to that wireless access point can hear each other. But if they can't, then you get a lot more possibility for collisions, because if computer one might be listening and doesn't hear anything, and if the computer one and computer two, if they're too far apart to hear each other's transmissions, but they can communicate with the access point, so they're still all good as far as connected to the network. But it could be that computer one and computer two don't hear each other, so they might end up in collisions a lot. So in cases like that, then this other additional handshaking mode might be employed, where the device first has to send a request to send to the access point. And if the access point says, okay, it's all good, then he'll send a clear to send and say you can transmit. Well, part of the message, the request to send message from computer one to the access point is how much data it has to send. And the wireless access point in the clear to send, everybody gets that clear to send because the access point is sending it. And that how much data is part of the message will be sent to everybody else. So everyone kind of has an idea how long they have to wait before they can try to do another request to send. Because, they know how long it takes to send, let's say, 1,000 bytes or something like that. So it, it can get pretty complex. They have to do a lot of calculations, but it's all kind of built into the hardware.
One, again, was first listed at verified to years.
Sorry, I'm repeating this.
Three, computer one must in a sense ask permission to transmit by sending a request to send message to the access point. The access point applied to the previous message. CTS message is heard by all other stations. Would find that another station is about to transmit, and they must wait before the conclusion. The amount of time to wait is part of the CTS message. Computer one now sends the data frame to computer two. Computer four receives the frame and sends it in off the frame to computer one.
Okay, so, it's inefficient, but, to make it work, that's what you have to do. It's actually amazing how well it does work with all that going on, with the acknowledgements and everything else, and the possibility for collisions, the fact that my Wi-Fi works, I can stream Netflix and Prime at the same time. So,
So this is current, that this isn't legacy.
no, this is current, this is how access points work. No, some of them have multiple antennas and all that, but that's a lot, usually because they've got multiple frequency capabilities, 2.4 gigahertz or 5 gigahertz. Some of them do have multiple channels now, like AC, 802.11 AC, which I think they call, is that Wi-Fi 7, I think? In any case.
13 channels?
802.11, well, 2.4 gigahertz has 11 channels in the US. Is it 13 or 14 in 14 in Europe? I really don't know why the difference has something to do with FCC.
The government
regulations.
reserves,
What's that?
the government reserves 2 of those channels or something like that.
Yeah, something, some FCC nonsense. Anyway, all right, so contention-based, controlled act, so that's your, Ethernet and Wi-Fi. Controlled access, again, there's not that much that's based on controlled access anymore, even though there's, there used to be some application for deterministic. Deterministic simply means that you can guarantee that each node will be able to send within a certain period of time. And so in a real-time system, like controlling like a factory floor or anything like that, anything where timing is critical, a deterministic system might have been used. My first job out of college, I was working for a company programming, and we were using ArcNet because we were doing control systems. We're doing HVAC control systems, and this was back in the mid-'80s. So it is a deterministic system because it's based on token passing. And with token passing, like Token Ring and ArcNet, you know how fast the token moves from node to node, and if the worst case scenario is every device has the maximum frame size to send. And so that is your worst case scenario for how frequently any one node will be able to transmit. Is if, all nodes have the maximum they can send, and there's 15 nodes, you can calculate that based on the speed of the network and everything. Ethernet is not deterministic because it's kind of free for all, but back with hub-based networks that matter. You could actually get a computer that hogged the network, so to speak, because it was faster than all the other computers and it just got the lion's share of the bandwidth. So that's not deterministic. Whereas, with Token Ring, everybody gets a fair share of the media. And that was important in certain types of systems. Nowadays with switch-based systems, it's, everyone gets the media whenever they want it. So it's not that important. Which is why Token Ring died eventually. I don't think we need to really go over that. We pretty much covered that.
Marty pointed out to me I was wrong. It's not 14, it's 11 channels
That's us in the United States.
in the US.
Yeah, it's in Europe that there's additional channels. So it is just, it's 13 in whatever. So there's 2 additional channels outside the US. There might be another country that does 11, I don't know. But might just be limited to us. Okay, so yeah, I don't think there's anything more we need to say about those. So I think now would be a good time for a break. So it's 20 till just about, so how about we'll resume at 10 till 7 by that clock. All right, so about 10 minutes.
Greg, real quick.
Yeah.
We have work to do.
Got more graders.
We're keeping up with stuff.
Oh, yeah. I mean, we're just getting back 10 years. At least 8.
Hey, me too.
Yeah. Then. If, when we talk about switches, you probably have heard most of it, but there is some new stuff to the 101. So hopefully I'll get through it by 8. I don't like to keep it longer than 8 anyway, because 2.5 hours is enough.
It's not a huge deal. It's just I did 16-hour day today. I've been over tomorrow.
Yeah, no, I understand totally. If you have to leave early, you just do it.
Much appreciated. I'm gonna take off.
Not here.
So you just,
I did not go
you
there.
don't already have one, only 2 people do.
I wasn't able to go.
So you just put your name on this and then
I haven't had a chance to talk
check
to him.
off what you did and the date and
My wife was out of town, so I had to
I'll
deal with my
assume that
kids.
you are telling the truth and I'll put my initials on there.
did all that's from last week. Yeah, were you for last week? Yeah.
Yeah,
Well, just the 2, just the first 2. Yeah, this has all,
We'll
we've only
see.
got
I
1,
mean,
2, 3, 4, 5,
Right now,
6,
it's like
7,
20%.
8. There's 11 total physical values.
Right now I have a
So,
0
put
on it.
all on.
You dropped me from a 91 to an 81.
Okay.
Yeah.
Okay, yeah. Make sure you do.
At least you
because the
weren't like
switches
at
are
C
probably
range to
a
drop
good
me
bit more
to D
important than
range.
this. I don't think we get into STPs. So it's not gonna be too complex coordination.
Yeah.
He got on.
Dude, I don't know how.
He was shocked. He was so shocked. He ran right into the damn door.
Smacked my face in the side of the door frame
I
on
was
my
like,
way
what
out.
happened? I thought you
Yeah.
like nailed it because I'm like, are you like shocked?
Yeah,
you
well,
nailed it or? Oh, dude, I got 100.
It literally freaked me out. My testing average in that class is like a 75, 80.
Yeah.
Thank you,
So
sir.
getting that was.
Like I told him, I was like, dude, you must have got like all the questions that you had no problem getting right and all the other tests. And it's just like,
Right.
rain. It was just your day.
It just worked out.
Hey, man, like I said, take the win.
Yeah.
Yeah, just take it at this point.
Oh, yeah.
I need all the help I could get.
Like, yeah. I'll take it. $6,000 later, okay.
$6 grand. Heck yeah.
Helped out a lot. Okay. Like surviving on money. Yeah, dude. savings and Pell Grant and. So
It helps, man.
got a lot of shit caught up, so what that did was just drop my outcome. And I just paid like 3 months of advance.
Nice.
Like, so I'm like, okay, great, I don't have to worry about it, I just have to worry about January.
It's the way to do it, though.
Plus I got half of the Christmas shopping right now. For the kids and all that shit. For daughter. It's 2 kids.
I'm lucky I'm the oldest of all my siblings, so I don't have nieces and nephews to get gifts for. I do have my cousin's kids that I need to get some gifts for. But I think I'll
Right,
just
Eric, you're not.
give my cousins some money and just be like, here, give them something for me.
That's what I could do with my niece. I'm like, oh, here you go. You want gift cards for gas or whatever? Here you go. Nope. Like 21. Knock yourself.
Damn, this thing cleared out.
Right.
Party.
Since I had company this weekend, I just like went to my computer last night at like midnight, of course. And it's like late on all these assignments. Oh. So I started just like jamming it. Assignments, and then I came in here like 3 hours before class and started just ripping through the labs, ripping through everything. I only have like 2 assignments that are still late that need to be done, but it went down considerably what I had. So I was like, thank God. And then like tomorrow, I'm just gonna finish it up. And then of course I forgot that chapter 10 lab.
Right.
And so I'm like, fuck, gotta do that.
Yep.
So.
Yeah, I saw that.
And then like next semester, I'm taking 5 classes.
5?
But
Obviously, he doesn't know.
Yeah, they're all 8
I
weeks,
don't
so
think
I'm
he was
like
trying
doing
to fall
3 in
through.
the beginning,
Huh?
2
I
at
don't
the
think he
end.
was trying to fall. through.
So
Good.
kind of splits it up. Still got a lot of course.
I thought you maybe you were taking them all at the same time. I was like, how are you gonna manage that?
Not to say I haven't done that before, where I've taken 16 units all at once.
Yeah.
But dude, yeah, it's you're like practically living in school without.
Mhm.
I don't like
I'm set up kind of the same way, set the opposite. I've got 2 classes in January and then that are 8 weeks, and then I have 3 when those are finished. 3 units.
Are you guys talking about this upcoming semester?
Yeah.
So I got 5 classes in the spring. I'm taking a summer school math course. And then I'm doing 4 classes in fall, and I only have like 3 classes in the spring, 25.
Mhm.
Just trying to get there. Seems like a long ways away, but man, I got so.
Yeah, just looking at, this is our 4th week in this class already. I was like, oh shit,
Yeah, dude.
after we're done with this.
And this is just, it's like, you know, they go through all the powers, but quite frankly, all the reading, all the exercise. Working on, you know. But we do it.
Yeah.
So I found myself on the hospital as a kid.
Going over to get in again.
Yeah, I have.
Yeah, they figured it out.
Graphic user.
Spread it out.
Just barely coming out with that. It was still like Windows 3.1.
Yeah, I can do a bunch of hands.
Taking on, man.
Yeah, how's graph three?
Like,
Alright,
it's just the
Got
network
another
coming
8-hour
in.
class at 6:30 tomorrow.
Alright, man.
Like
Have a good.
reallocating bits and shit. Yeah, that's. I'm just. Yeah, it might as well be in Chinese.
I'm gonna have to.
I got off of
Yeah.
work, I'm free, so
I'm gonna
I
have
just went home, made some food. So now.
Is that netting problem? I just did it. Like,
I was
so I
watched
didn't
last
take a
night,
zero.
doing homework at the same time.
And he said we could look it
Didn't
up,
get to
so,
bed till about 7 a.m. And then
but it's, I'm gonna have to.
about 4 hours,
Just like, you
got
know,
up, fluffed laundry, last load, took it over to my girlfriend's place, got her to work, took care of the kid.
Somebody posted
Takes a while.
a series.
Came over here.
From students. Got copies. I wanted like 8 hours of that. But still, like,
Oh my gosh.
yeah,
I didn't tell you, but I went there.
yeah, same.
It's good, man. I when I saw it, so I sit down on the corner, I was about to be like, "Oh, what's this?" And so I was like, "Oh, wait."
I was like, who are you again?
Home costume and that way.
Gotcha. Oh, man, that's tomorrow, isn't it?
What? Yeah.
Halloween. I'm so exhausted.
And they're already like,
Oh, I work retail, believe me, I know.
yeah, I'm like, before you know it, June's gonna be when they advertise.
Wait, for the day after, let's just start playing Christmas music in 2 days.
Yeah, dude. All right, now.
Scourge of Mariah Carey. Oh, I know. Every time I hear that damn song, I just want. Oh, yeah. That's true. Oh.
I try to follow it. Right, me too. Yep. Seems like he like cares if we're following. Exactly.
All right, we'll talk a little bit about the data link frame, just a few more slides in this chapter. Module, we call them. Okay, so unlike all the other encapsulations, the frame has both a header and a trailer. So it's the only one that has a trailer. And the trailer is the CRC, right. So it's really the only one that does, you know, the other headers have checksums. And depending on which header it is, the checksum may be used to, it's used to really just to verify the header information, that the header data hasn't been changed. Whereas the CRC on the frame checks everything. It even checks the source and destination address. So the entire frame, all the bytes in the entire frame are used to calculate the CRC. And that's your trailer. It's 32-bit value that goes there. All right, so the fields that are in the header, now the trailer is just, you know, the error correction code. The header might vary depending on the underlying protocol. So in this diagram, first off, there's a couple of fields that are not part of the frame in the sense that you can see it in Wireshark, okay? You'll never see the frame start or the frame stop in Wireshark. You actually don't really see the CRC either in Wireshark. But the frame start is really just a pattern of bits that tell the receiving device, here comes a frame. And the frame stop is another particular pattern of bits that say, that, this is the end of the frame. And everything in between is your actual frame data. So Ethernet is going to have addressing, destination MAC, source MAC, and a type field. Does not have a control field. Other protocols might have an additional field in the frame header. Wi-Fi might, for example. I can't remember. I have to go back and look. Don't think we actually look at the details of a Wi-Fi frame that include the extra stuff. I think it might have some sort of control field in it as well that identifies like access points and things. But in any case, Ethernet, wired Ethernet is just going to have the addresses in the type field, which tells basically it's so that the device driver, because this has to be done in software, it's so that the device driver knows what process to send this frame to. Is this IP or is this IPX? Or is it IPv6? Is it, IPv4 or IPv6? Is it IPX or even some other a layer 3 protocol? So that's very important because, without the type field, we wouldn't know when the frame got there, what upper layer protocol to send it to. And, if there was a control field in certain technologies, not Ethernet, then there would be an additional field. And then the data. And the data, that word is being used loosely. The data really means the entire packet, along with, packet header, segment header, and then the data. But from a frame standpoint, it's all data. So the addresses also referred to as the physical address, and it's used to deliver the frame on the local link. That is all you got. That's one thing that you need to be aware of, is that those MAC addresses have no meaning outside of the land that they originated in, because they get stripped at the router, because a router is the only, is a layer 3 device is what's going to get the frame to a different LAN. So they have the frame headers don't have any meaning outside of the local LAN. It's, even though, they put in controls to prevent network interfaces from duplicating the MAC address, it wouldn't be such a big deal if there was duplicate MAC addresses, unless they happen to be put on the same physical network, the same, not broadcast domain, but the same, same broadcast domain. So if they were put on the same broadcast domain, that would be a problem. But I could have a device in here with a MAC address with totally identical to a computer out in the computer commons, and it wouldn't affect anything adversely because we're on separate broadcast domains. The devices outside of the CNT network, the 172.31/16 network, they'll never be seen by any other networks. So they only have local significance. Okay. Not really much more to say about that. So the logical topology that is used and the physical media is all dependent on what is your, say, going to the TCP/IP model, what does your network interface layer look like? Or what does your data link / physical layer look like? Because all of these technologies pretty much define the data link layer and the physical layer. They define the lower 2 layers of the OSI model. Ethernet because Ethernet defines, you know, certainly the data link layer, MAC addresses and all that, but also it will only run on, you know, certain types of media at certain speeds and certain distances. Wireless, of course, you know, defines that the media must be the airwaves. Point to point, that can, depending on what type of point-to-point network it is, could be a variety of media. HDLC and frame relay all have different types, media types that they might be utilizing, but they're well defined by the standards that define those technologies. The data link and the physical layers are defined by the standard definition. Okay, and that's pretty much it. The only ones that in this class we study, Ethernet and 802.11 wireless. We talk a little bit here and there about point-to-point stuff, but we don't do any HDLC or frame relay. Frame relay we used to do a long time ago, back in the fourth class, when there used to be 4 CCNA classes, and they pulled pretty much all the WAN stuff out. It's now all in CCNP. And frame relay is a more or less a dead WAN technology anyway. As is HDLC is sort of, it's almost like a physical layer technology. Anyway, we don't need to worry about them at all. So, okay, so that was module 6, and we'll move right on to module 7. All right, so you learned a fair amount about switches, I hope, in CNT 101. We're just gonna review some of that and go into a little bit more. The forwarding methods, I think we even talked about that in CNT 101. So there really isn't gonna be that much new information here. So hopefully you realize that switches work at the data link layer. And whenever you say a device works at a certain layer, when we're talking about a networking device, they work at that layer and below and all the others. Obviously, a router is a layer 3 device, but you know, it has to have a network interface and has to have physical connectors and everything. So it works at network and below. Switch just works at the bottom 2 layers. And then certain devices like gateways work at like really the transport, or even all 7 layers. A computer, for example, works at all 7 layers because it creates the data. So and using user programs or user applications, and those are given off to the application layer on the computer. So anyway, data link and physical layer. I honestly don't remember. You might need to remember that 802.2 specifically relates to the LLC part of the data link layer. So this is basically Ethernet, and this is kind of going to be more, it still has to do the same things, you know, because it's defined in a standard. So all of them have to do the same things, but it'll be usually software component, and the software will be written by somebody specifically for a particular type of device. So LLC is going to do something based on, you know, what type of NIC this is, or what type of switch this is, or whatever. Okay, so again, we keep seeing these standards. Those are all data link layer standards, and then they all sit below the LLC sublayer. Again, device driver is the best, you know, and it may not be that there's overlap with what device drivers do. They may do some LLC and a little bit of Mac sublayer stuff, but for the most part, this is your hardware and this is your software, part of the data link layer process. Ethernet addressing occurs, so there's not that much new so far. We know all this MAC addresses at the data link layer, error detection with the name of the field is called the FCS, and it contains the CRC. Because the CRC is just a calculation. This FCS is the field name of the frame.
FCS is frame check sequence.
Yes. Is that the same? Yeah, it is the same. Battery dying in this thing or something? Okay. Yeah, so none of this is new, talking about bus topology, CSMA-CD. Today's networks use full duplex switches. So we don't even care about CSMA-CD in those situations. It's getting annoying if this thing doesn't have it. All right, so Ethernet frame fields. Again, nothing really new here. Preamble and start frame delimiter is just a pattern of bits, 8 bytes in length that says, hey, here comes a frame. And then they don't mention it here, but there might be a end of frame sequence as well. But the 1518 bytes is only from here to through the FCS. So the 1518 and the 64 byte minimum does not include the preamble and SFD, start frame delimiter. Okay, so just the frame as we know it has to be between 64 and 1518. And that's where they're talking about fragments from collisions, or you can also get fragments from, let's say misbehaving network interfaces. If there's something physically wrong with the NIC, you can it'll start just spewing out data sometimes. And those might be interpreted as fragments or runs. So anything less than 64 bytes is considered a invalid frame. Anything more than 1518 is considered 1500 bytes of data. And the 18 comes from the fact that there's 6, 6, 2, and 4. That's where the additional 18 comes from. So if you get if a device gets a frame like that, then boom, they're dropped. Unless they're supporting jumbos. But as far as I know, there's no such thing as supporting frame sizes less than 64 bytes. But there is, as I said before, the possibility of larger than 1518. Okay, 48-bit addresses is the MAC address using hexadecimal digits, 12 of them. And they're broken up into 2 parts. What are the 2 parts of the MAC address? 24 bits and 24 bits. What's the first 24 bits?
The unique identifier.
Mm-hmm. The OUI, it's called, organizationally unique identifier. So, and then the last 24 bits are serial number. So the way it's supposed to work is that if you want to manufacture network interfaces, then you have to go to, can't remember if it's which organization it is that sends out, that gives you the OUIs. But you have to go to somebody and say, I need an OUI. And they'll give you a 24-bit hex number. And it's your responsibility then to make NICs that the first 24 bits are that OUI that you were assigned, and the last 24 bits are unique for every device that you create. And that is supposed to guarantee, that there's no duplicate MAC addresses out there in the world. However, I can see, the way things work nowadays, that 24 bits is, I believe, how many can you make? See, 32 bits is 4 billion. 24 bits, I think, is 16 million. I think 24 bits, you can make a number that is up to 16 million. So that means in the history of networking, there can be 16 million unique manufacturers of network interfaces. And each one can make up to 16 million network interfaces. Now, it seems like a lot, but, think about, VMware for, when you talk about virtualization, we have at any given time, certainly hundreds, if not over 1,000 virtual machines somewhere. They may not all be running at the same time, but they're, in memory or, in storage. And so you could see where, you'd run out of MAC addresses VMware has their own OUI. They actually have a bunch of OUIs because they, they're in virtualization and they need to be able to produce a whole bunch of unique MAC addresses. But you could see that, there's not inconceivable that you could run out of MAC addresses. Anyway, I haven't heard that it's a problem, so maybe I'm wrong about that. But I also haven't, looked to see if anyone is reporting on it being a problem. So who knows? Okay, so MAC addresses are usually just a string of 12 digits. There might be a dash in between. There might be a colon in between each pair of digits. Occasionally, you'll see a dotted number where there's 4 hex digits, a dot, 4, and then another 4. So there isn't a real standard way to represent hexadecimal or MAC addresses. I've seen them 3 different ways: with dashes, with colons, and that's in between each pair of digits. And I've seen 4 digits separated by dots, and sometimes just all 12 run together. Okay, so OUIs and the vendor assigned. So I work for a computer, an embedded systems company. They did hardened hardware and they, sold to industrial applications, military, things like that. And this was the late 80s, actually 89 is when I started there. So into the early 90s. And they were, they were developing their first Ethernet card. Ethernet was pretty, in its infancy then. Twisted pair was just becoming a common thing. The previous company I worked for set up a network using ThickNet, 10^5, and then 10^2. In any case, our first customer, I can't swear it was our first customer, but I'll try to remember. One of our customers was Disney. They were actually developing the Tower of Terror, and they need to communicate between the floors, and they were going to use Ethernet. So they, bought a bunch of our cards for development purposes, and we shipped a bunch of cards with all that had the same MAC address in them. So they were like, "Well, we can't communicate on," nothing was working, and so I sat up all night with one or two other people. Back then, there was like a little what we call PAL, a programmable array logic, was a little chip that held that MAC address. And thankfully, we had a device to burn, new data into it. So, kind of like a ROM. And so we sat up all night burning unique addresses into, I don't know how many, it wasn't that many. It just took a long time to figure out how to do it. And so we shipped them out, the next morning. I think we actually went to airport and went, plane to plane because they needed them immediately. So, but yeah, we shipped a bunch of NICs with identical MAC addresses. Somebody screwed up there. Anyway, so yeah, things don't work if the identical MAC addresses are on the same LAN. Frame processing. Let's see. Yeah, I pretty much covered that in the simulation, the animation that I showed you. So the NIC is sort of like the gatekeeper for the device. If the MAC doesn't match its burned in address and it's not a broadcast or a particular type of multicast that the device cares about, it just gets tossed by the device. It says, this isn't for me. Doesn't even matter if the IP address inside is correct. It'll never even look at that. It only looks at the MAC. The NIC only looks at the MAC address. Doesn't care about anything inside. When it's determining whether the device is, whether the packet is for frame is for it or not. Okay, so unicast means, it's a MAC that belongs to a particular device. And the MAC addresses are learned by source devices, the ones that are going to be sending a frame using the ARP protocol, address resolution protocol. So in order for a MAC to be learned, of course, you need an IP address. And IP addresses are usually learned by domain name lookups. So at least, unless you're, your IP addressing scheme, I usually ping IP addresses more than names. I actually remember the IP address of most of our servers better than I do the names of our servers. But, in most situations, you're communicating with the name of a computer. It gets translated through DNS to an IP address and then to a MAC address through ARP. Now that's only if you're sending to a device on your LAN, right? If there's a router in between, you only care about learning the MAC address of the router. And you just, use your default gateway configuration to do an ARP to get the MAC address. In IPv6, you still have to do the same thing. MAC addresses are MAC addresses. Doesn't IPv4, IPv6, they don't change that. That's why the layered architecture is so effective, is we can completely change the network layer like we did with IPv4 changing to IPv6. It's vastly different, certainly as far as the addressing goes. But a lot of things are different about it. But nothing changes here. What does change is the process of taking an IP address to get a MAC address. In IPv4, we use ARP using a broadcast. In IPv6, there's no such thing as a broadcast. In IPv6, there's only unicast and multicast. So there's a specific type of multicast called a neighbor discovery that is used by IPv6 to learn the MAC address. And it's not that really different than our neighbor discovery is a multicast. It's an all nodes multicast. So effectively it's a broadcast because the switch will send it out to all ports. But it's not a broadcast in the sense that it's got, all Fs or whatever as the destination. It's a particular type of multicast. Okay, so that's unicast MAC addresses. Broadcasts, are all binary ones, 48 binary ones, or 6 or 12, I mean, Fs, hexadecimal Fs are to make a broadcast MAC. And then broadcasts can also be shown up as IP address broadcast, and that's all 255s, 255, 255, 255, 255. Either way, it's all binary ones. So Ken, this is only IPv4. There is no such thing as a broadcast in IPv6. So a multicast MAC address. So just like there has to be a broadcast MAC address so that devices are aware that this is supposed to go to everybody. The same thing with multicast packets. There's got to be the NIC has to know that this is a multicast MAC address. It won't be the address of the device itself. It'll be a special, you know, it'll look like this. The first 24 bits will look like 01005E. Okay, so every multicast frame, the first 24 bits will have that pattern. And then the next 24 bits are the specific application for the multicast. And whether the device listens and processes that multicast will depend on whether some application has registered the second 24 bits and basically told the data link layer, yeah, I need you to process if it has 000C8 in the destination MAC. And if, you know, these guys apparently, you know, they're not listening to 00C8, but these guys are. And so they'll get, upper layers will get those frames and these guys won't. Okay. Oh, okay. So yeah, so there's particular, you know, there's particular arrangements for IPv6 as well. If it's an IPv6 multicast, then the first 16 bits of the frame will be 3333. So that tells it. So 01005E is for IPv4 multicast, 3333 is for IPv6 multicast. And there's others, you know, there's a lot of reserved multicast addresses out there. You know, they'll still start with the appropriate bit pattern if it's V4 or V6, but the last 24 bits will be different based on the application. So routing protocols, for example, RIP version 2 uses multicast instead of broadcast to get everybody, you know, aware of, you know, here's a RIP packet. OSPF, pretty much all the routing protocols use some sort of multicast to communicate with each other. Spanning tree protocol, which we'll talk about later, it also has a special multicast address. Now, normally, how does a switch handle multicast? Without doing anything special, if the switch doesn't support it, or if you haven't configured the switch to specifically support multicast groups, then a switch will just treat it like a broadcast. That guarantees that whoever was supposed to receive the multicast will get it. Yes, additional data gets, gets sent that doesn't need to be sent. These guys didn't need to get the data, but unless you've configured the switch for what's called IGMP, then the switch will just forward out a multicast as if it were a broadcast. IGMP will allow devices to register themselves with the switch to say, hey, I'm running some multicast some multicast application, with this 24 bits is my identifier. And then the switch will know, okay, port 6 should get these multicast packets. But if you don't do that, if you don't configure the switch to allow that, then it'll just treat it like a broadcast. That's what the term flood means. Flood means sent out all ports except the one that it was received on. They're not forwarded by routers unless specifically configured to route multicast. So by default, routers will not route multicast packets because they don't really know what to do with them. They're not 224 is not a recognized, IP address in terms of, being addressed to a host. So you'd have to specifically configure a router to support that capability. All right, MAC address tables. Hopefully you at least learned a little bit about what they are. They are a table that the switch holds or creates actually on the fly. What does the switch use to create its MAC address table? What does the switch use? How does the switch create its MAC address table?
It reads the source MAC address.
Yep, reads the source MAC address of every incoming frame. And now, depending on how the switch is configured, but most likely it takes care of business first by getting the frame to where it's supposed to go, because that's highest priority. But at some point in the process, it takes the source address of the frame that it just processed and goes and looks in its MAC address table to see if it exists. If it doesn't exist, it adds it to its MAC address table. If it does exist already, what does it do? Does it updates it with what?
Time to live or whatever.
Yeah, the timestamp. Exactly. Time, like a time to live.
I'm confused as to why it's the source it's reading and not the destination. Like, oh, it goes here, so I'm gonna put this in my table now. You know what I mean?
Yeah, well, it doesn't know where it's supposed to go until it has the entry in its table. So, yeah, if you have an incoming frame, let's say you just turned on the switch, it doesn't know anything, right? They're not pre-programmed with any kind of MAC address table. So it's empty. So the first frame it receives will have a destination and a source, right? Destination and a source. Well, the destination, it does a lookup and there's nothing there. There's nothing in its MAC address table. So it can't find it. So what does it do in that case? So it gets first frame it's received, has no MAC address table yet. What does it do with that frame?
Okay.
Yeah. Floods it out all ports. Okay. So it doesn't know what port the destination lives on. It only knows where it received that frame. It received that frame from port 4, let's say. So it puts in its MAC address table, source MAC address can be found on port 4. Okay. Now, when the destination responds, now he's got another MAC address. And he says, okay, whatever the source is of the next frame that came in from the response, that came in on port 8. So it makes a new entry. This destination, this MAC address is on port 8. And then it knows where the destination is, assuming it's responding to the guy that just sent, because he just built that entry in the table and he knows it goes out port 4. So that's how the table gets built. Until the entry it gets built, it just floods it out to all ports, because it's not going to assume just because it doesn't have it in its MAC table that it doesn't exist. It's going to assume it does exist. And if it does, it'll learn real quick where it is, because presumably it's going to respond. And it can, then build that entry. And you can have multiple entries per port. With trunk ports that happens. And if we were to attach another switch to a port on a switch, connect 2 switches together, then all the devices from switch A will be registered as on port 12. If we plugged it into port 12, will be registered as on port 12 of switch B. If you had that kind of arrangement. So yeah, you can have multiple MAC addresses per port because of that, because you can connect the devices together. Okay. Oh, CAM, content addressable memory. This is part of what makes switches so fast. So in a big network, you might have thousands of, well, maybe not on one broadcast domain, but certainly you could have hundreds of devices. And, while the switch computers are pretty fast and can search pretty quickly these days, even, a couple hundred nanoseconds per frame slows things down tremendously, because there's millions of frames going through these switches, on a daily basis. So even if it's a very small amount of time that it takes to search its MAC address table to find the destination, that adds up. So it doesn't do a traditional search where you basically have, okay, I have address ABC. So I'm going to look in, I'm going to look in the first entry 1 of my MAC address table, compare it to ABC. Okay, that's not it. Look in entry 2, oh, it's found on entry 26. Okay. It doesn't do that because that would take a lot of time. So this content addressable memory, it basically uses the value of the MAC address. And that value, it does some sort of hashing routine. That value ends up to be an index into the switching table, the MAC address table. So let's say I had address ABCD. I run this hashing algorithm on it, and the hashing algorithm, generates location 115. So I'll store MAC address ABCD in location 115. And then, the next MAC address is 1B2F. And I run the hashing algorithm, and it might create a value of 56. So I'll store that MAC address in location 56 of my table. So now whenever when it gets a destination address of ABCD, it runs the same hashing algorithm on the data and goes right to location 112, because that's where the hashing algorithm says it goes. And much, much faster than doing a linear search of each entry. And that's basically what content addressable memory is. It's just very, very, it uses the data to index into the location. You can actually do that, if you're like a programmer. I remember a database exercise back in college. We did something very similar to that, where, we did a bunch of linear searches, just like I was saying before, and would see how long it took, to search 1,000 entries. And then we used some sort of hashing algorithm to use the data on the key value of the database record, and it was like instant, the searching. So it's a real effective method for storing certain types of data and retrieving it quickly. Okay, so we know that the source MAC is examined. If the entry already exists, now one thing that it has to do besides update the timestamp, if the entry already exists, also has to make sure that it's still in the same port, right? Because you may have just changed the cables, and just because that MAC address exists doesn't mean it's in, that it's still in the port it used to be in. So it has to check that too. It has to verify that it's still where it's supposed to be. And if it is, then it updates the timestamp because, again, they age out because it's first off, devices are turned on and turned off. They get switched around. So it doesn't want to have a static MAC address table because they'll change based on, different conditions. So they probably keep them in there for quite a long time because I think a typical network, people aren't constantly changing the cables around. But, probably on the order of several minutes is how long it keeps them in the MAC table before aging them out. All right, and then the forwarding process is finding the destination MAC and forwarding it out the appropriate port or flooding it if it can't be found. Okay, so frame forwarding methods. There's basically two major methods, and then there's a couple subcategories of cut through. But store and forward switching is the most reliable, but the slowest. It reads the entire frame in, verifies the CRC, verifies that it's not a runt or a giant, and then forwards it on to the outgoing. Okay, so it's reliable in the sense that it's not going to be forwarding error frames. There's no sense in forwarding error frames because they're errors. But that means more processing. You've got to, read the entire frame in, do the CRC calc, and then forward it. And then cut through switching is the fastest. It starts forwarding the frame as soon as it gets the destination, it reads in the first 6 bytes, the destination MAC address. And so it starts the forwarding process while the frame is still arriving. And the problem with that is that it could be a runt. It could have a CRC error. It could be, any other type of error, a giant or whatever. And the switch will never know. Doesn't know, doesn't care. It just forwards it as fast as it can. So very, very fast, but it will propagate errors to the rest of the network, which you may or may not want. Quality of service is necessary. Store and forward is necessary if you have quality of service enabled, where like voice packets have to be treated differently because it's going to have to examine some aspect of that frame to know that this is, to be treated with some sort of prioritization. But for just regular data frames, cut through will work for the most part. And really, nowadays, the number of errors that you're likely to see is pretty small. I mean, I look at the statistics every once in a while on our switches and routers, and usually it's 0 errors. Back in the 90s, when I was IT director for a community college, a little bit smaller than this one, we were still, doing hubs and collisions and the error count was just astronomical. I mean, there'd be tens of thousands, if not hundreds of thousands of errors, mostly because of things like fragments caused by collisions. And that's just because our network was a mess until we redesigned it. But it was a big mess. Okay, so that's the two main categories. In the category of cut through, there's two subcategories. Fast forward is the fastest, that does just what I described, which means it starts forwarding as soon as it reads the destination. And then if there's errors, it doesn't care. The end device will detect that there's an error on the frame. Fragment free is just what it sounds like. It will read in to make sure that at least there's 64 bytes of good frame. And that means it's not a runt, it's not a fragment. But there could still be a CRC error, or it could still be a giant or something like that. But that's kind of a compromise. Fragment free is kind of a compromise between fast forward and store and forward.
What kind of speed difference are we talking about?
Yeah, I don't know. They're so fast nowadays because the processing in switches is done with a VL, what do they call it? Very large semiconductor, something integrated circuit, something that I might got the acronym wrong. But anyway, in hardware. So this actual process of switching is done in hardware very, very fast. Because it's a pretty simple process for the most part. And so they just took, the algorithm for switching and turned it into an integrated circuit, specialized integrated circuit. The fact that you've got an iOS that loads and, that's clearly software, that's all for management purposes. That's not, the iOS does not do the switching of the device. It doesn't switch the frames. It's just used to configure aspects of the device. The actual switching process is done in hardware. And I don't really know. I don't know the difference. I would imagine it's somewhat significant, but I couldn't attach a number. It'd be something you could probably look up and get, some kind of answer. And of course, it'll depend on what type of switch, what level, enterprise versus, something you bought for $9.99 at Walmart or something. They're not going to be quite as fast. And they're likely, those low end switches are likely to just do store and forward anyway. Not store and forward, I'm sorry, cut through. Because, it takes extra processing to do store and forward. So they're most likely to just do the cut through because they're probably not very fast anyway. Now, some switches, from what I read, they will automatically switch. They'll start out at cut through, but they'll also somehow I'm not sure how this is done, whether it's like they take a sampling of incoming frames or something else, but they somehow maintains some level of statistics as to how many error frames are going through the switch. And if reaches a certain threshold, they'll switch to store and forward. And so that way they, go as fast as they can with cut through until it's determined that, hey, we're seeing a significant number of error frames, so we're going to switch. But, they can't be checking every frame because then that wouldn't be cut through. So it must be like a sampling. I'm not sure exactly how it works. Okay, one other aspect about the way that the switches are designed, port-based versus shared memory. So port-based memory means that each port has a certain assigned memory buffer packets or frames to buffer incoming and outgoing frames. So once that buffer space fills up, then you're going to start dropping frames. So it is, I'm pretty sure, the less expensive way to do it. And so your lower end switches are more likely to do port-based. The problem with port-based is that in most networks, you've got a bunch of, end devices, and then you've got maybe a server or two. Like a small business network is likely to have several end devices and then one or two servers. Well, the majority of your frames are going to be sent to that server, presumably. And so it could be that, you're not making good use of the port-based memory and overloading, port-based memory on the end devices, but you're overloading the memory on the port where the switch can be found. So shared memory takes care of that. It basically, allocates the memory based on who needs it. And so there's a common memory buffer that's shared by all the ports, and it's dynamically allocated based on need. So that way there's no, separate sets of memory. There's just one big memory pool, and from the incoming port, they get put into that memory, and they go directly from that same memory space to the outgoing port without an intermediate storage place. So shared memory, larger frames that can be transmitted with fewer drop frames, asymmetric switching, I mentioned, where you've got one or two ports that are getting, receiving the lion's share of the data.
So with the asymmetric switching, it's saving bandwidth, but it would be taking up some sort of processing power, wouldn't it? Keeping track of what bandwidth is needed somewhere.
With asymmetric switching?
Yeah.
Wait, so repeat your question again?
So it's saving bandwidth, but it would require more processing from the switch itself, wouldn't it?
I don't think really processing, because, well, there might be, because, they've got a little bit more work to do with the dynamic linking of each frame and shared memory to the port that it's supposed to go out to. Whereas with port-based memory, it's dedicated space. And so they just have to get it to that memory space to get it out to that port. So so in that sense, there might be less processing with port-based memory, but this is still, shared memory is going to be more efficient, because you're less likely to overload, less likely to run out of memory and start dropping frames, because if one port needs more memory, because it's like where a server is connected, and so everybody's sending data to that server, and then you just allocate more of the shared memory. Whereas with this, once it's gone, it's gone. Okay. This last couple of things aren't very duplex and speed. I don't think there's much to say about that. You know what full duplex and half duplex is. Usually you don't mess with it. By default, switches running full duplex. You would have to go in and configure them for half duplex, or if some device that you plug into them can only operate half duplex, the switch will auto negotiate that mode. Oh, okay. I thought it was 10 gig. So gig, oh, right, of course, yeah. Gig uses all four pairs for transmit and receive simultaneously. So they can only operate in full duplex. So gig and above, gig and 10 gig can only be full duplex. It's only 100 meg and 10 meg Ethernet that can operate in half duplex. Okay. Again, that's because with 10 meg and 100 meg Ethernet, only 2 pairs are used of the 4 pairs in a twisted pair. And so, you can just say, okay, transmit on these 2 and receive on these 2. And if it's half duplex, do one or the other, but not both. With gig, all 4, they're bidirectional, basically. All 4 pairs or all 8 wires are in use, transmitting and receiving simultaneously. How they do that is a wonder of engineering. Because you would think if you're transmitting simultaneously, you're going to get what the old-fashioned collision, right? But there's something I tried to read a white paper on it a long time ago. They use something called canceller, what do they call something cancellers. Basically, the encoding for the transmit end and the receive end are different encoding, and so it's like the bits miss each other somehow in the timing. I'm not an engineer, electrical engineer, so I don't fully understand it, but somehow they make that work, which is kind of amazing. Yeah, I don't think, we know full duplex and half duplex can't coexist on the same link, so they're not going to link up. If you force a device to half or half duplex, then the other device, the auto negotiate likely will not work. So you'll probably have to force the other device, the other end, to the same duplex mode. So when you set half or full duplex specifically, you're essentially turning off auto negotiation, which means both sides have to be supporting the same mode. Now, auto MDIX is what we talked about, where you can connect 2 switches together, or a switch to a hub, or hub to a hub, and you can use the wrong cable and it works. Right? Normally, switch to switch, switch to hub, you got to use what type of cable? Crossover. If both sides support auto MDIX, they will actually, if only one side supports auto MDIX, they'll switch the transmit and receive lines in hardware internally, and you can use the wrong cable to connect the 2 devices together and it works. And most modern devices support auto MDIX. Says it's default on switches running iOS 12.2 and above, and that's pretty old. So it's been around for quite a long time on Cisco devices. All right, that's pretty much it. It didn't talk, I don't think, too much, or I might have missed it, about the speed, setting the speed. Normally, you use auto negotiation for that as well. You don't want to force it to a particular speed unless you have to. The 2 devices will negotiate the fastest possible speed and the best duplex mode. But occasionally it fails, or a device doesn't support auto negotiation, and you've got to, then set your device. I run into that just very, very rarely today. Used to be a little bit more frequently 20 years ago, but not today. Okay, so we'll see you Wednesday. Zoom people, we're only doing lab on Wednesday since we finished the chapters. So you don't need to Zoom in. I won't even start the Zoom session unless there's a reason for it. I know that somebody asked about starting the Zoom last Wednesday when I wasn't here. Was that anybody that's on tonight?
Yes, that was me. I didn't realize it.
Okay, is there a reason that you'd want to, because all you're gonna do is see like,
No, I didn't know it was just
Over the
labs on
Wednesday.
Wednesday.
what's that?
I didn't know it was just labs on Wednesday. I tuned
Oh.
in thinking we were gonna do extra stuff.
Okay, well, check your announcements. I did send an announcement last Monday about Wednesday that we're only gonna be doing lab on Wednesday. Or maybe I
Okay.
sent it Tuesday. But in any case, I'll usually send an announcement. I'll do that tonight as well, tonight or tomorrow. Send an announcement out to Canvas, letting you know that we're just doing lab in class, so you don't need to zoom in.
Okay.
Okay?
Thank you.
All right, see you. So you Zoom guys, you're welcome to come in on Wednesdays, by the way, if you want. But you could, also open lab day or any of the other